So in problems where we are given a rate of change, and you're expected to determine some kind of like net total, then what we've been learning about integrals is going to allow us to write an accumulation function. So the function that describes my rate of change is going to go in the integrand. The lower bound of my integral is going to be the start time. Normally that's like 0. Normally that's t equals 0 unless the problem tells you otherwise. But the upper bound of your integral is basically like the end time. Like when are you interested in figuring out how much you've accumulated? So these are just application problems now. We've learned about integrals. We've learned about how to calculate areas using integrals. Now we're just, finding other applications for the integral. Like this one says, water flows into a storage tank at a rate given by this function. So this function is a rate of change. Change of what? Yeah. It's a rate of change of the volume of water in the tank. So the question says, if t represents time in hours and f represents the flow rate of water, at the end of the day, how much water is in the storage tank? So to answer this question, I'm going to set up an integral. What's my lower bound? 0. What's my upper bound? 24. And then the integrand is going to be my rate of change. And what's that antiderivative? Arctangent. So we have arctangent of 24 minus arctangent of 0. You got 1.529 minus 0. And that's in thousands of gallons. 1.529 thousands of gallons of water in the tank. But if I have some quantity and I take the derivative with respect to t, the derivative gives me a rate of change. That's what we defined as like the derivative with respect to time. The derivative with respect to time is the rate of change. So if I'm given some quantity and I take the derivative with respect to time, that tells me the rate of change of that quantity. Today what we're doing is we're given a rate of change, and we are now taking the antiderivative with respect to time to get back to a function that describes the quantity. Do you see how those ideas are related? Yeah. This one says, the culture of yeast in a fermentation drum is growing at a rate given by the following function of time. Let t represent time in hours and g represents the rate at which the yeast population is growing. At the end of 10 hours, how much yeast is in the fermentation drum? So what should I do?
Integral.
Yeah, make an integral. From
10, 0.
Yeah, lower bound 0, upper bound 10. The integrand is going to be my rate of change. And the rate at which the yeast is growing is the rate of change of the yeast population. So a couple of things. For one, 1.733 is just a constant. So I can take the constant outside of the integral. It's something we're always allowed to do. And the other thing is I would like to make a little u substitution here. Where I set u equal to 0.3466t. So when I want to replace 0.3466t, I can replace that with u. When I want to replace the dt, I need to replace dt with du divided by 0.3466. Do you see why? I want to replace dt with du times 1 over 0.3466. Now I need to calculate my new lower bound, because this is substitution, right? And so the new lower bound is like I plug in the 0 old lower bound into t here, and then that's 0.3466 times 0. So my new lower bound is still 0. I plug in 0. And then whenever I plug in t, my old upper bound, or sorry, when I plug in 10, the number 10, over here for t, I get 0.3466 times 10, which is 3.466. So now 1.733 divided by 0.3466 times, what's the antiderivative of e to the u?
E to the U.
E to the u. Lower bound 0, upper bound 3.466. Go ahead and divide. I'll just write 0.6007 times e to the power 3.466 minus e to the power 0. I know e to the power 0 is just 1. So in my calculator, I'm going to type in 0.6007 times, open parentheses, e to the power 3.466 minus 1, close parentheses. My calculator tells me that number is 18.63. I don't know what units that is. I guess that's fine. Units of yeast, some kind of unit. Grams, pounds, who knows? All right, any questions about how we did that? Maybe you don't need to do the U substitution thing if you get enough practice with these things. Like, honestly, I was doing the U substitution step by step to show you guys, but you could also think about this. You know, if I've got the antiderivative of e to a constant times t, that's always going to be 1 divided by k e to the kt. Because think about taking the derivative, right? Think about reversing this. If I were to take the derivative of e to the kt, it would be k times e to the kt, so the k divided by k cancels and you get back the integrand. And so this is it. And if you know this, then you don't have to do the substitution part, right? If you know that antiderivative, you just know I'm gonna do e to the, what is it? 0.3466 t, and then also divide by 0.3466, like that little rule says. So you get the hang of these things. You sort of figure out which problems you need to write out the full U substitution for and which ones you can kind of just eyeball. Everything takes practice. All right, fans enter a football stadium at a rate given by the following function of time. So this is the rate of change of the number of fans in the stadium. Let t represent time in minutes. T equals 0 is the kickoff, and F represents the rate fans enter the stadium in fans per minute. By 30 minutes after the kickoff, how many fans are inside the stadium? So the stadium is accumulating fans. How do I set up this problem? Yep, the answer is going to be an integral. Yep, from lower bound -90, upper bound 30. So fans start entering the stadium an hour and a half before kickoff. And we're interested in how many fans are there 30 minutes after kickoff. So now my integrand will be the rate of change, 165, times sine of pi over 120 t plus 3 over 4 pi dt. So let's do a U substitution again. This time I'm going to say U equals what?
Pi over 120 equals 3 pi over 4.
Perfect. Yeah, because when we do a U substitution, we're kind of looking for functions that are inside of other functions. I'm looking for a function composition in my integrand, and then I grab the part that's inside. So I do pi over 120t plus 3 pi over 4. So the derivative of u with respect to t is going to be what?
Pi over 20?
Pi over 120, yeah.
Yeah.
So I can replace the dt with 120 divided by pi times du. So we'll do that. Go ahead and rewrite this integral as 165 times 120 divided by pi times integral from negative 90 up to 30 of sine of u du.
Wait, do we need to get the new?
Yo, you're right. Thank you. Man, I forget that like literally 50% of the time. It's such an easy mistake to make. Yeah.
Okay, so what I did was.
So I need to use this formula to get my new lower bound and upper bound. I'm going to plug in the lower bound. So let's say t equals negative 90. If that's negative 90, that's negative 90 over 120, which is negative 3/4. So when I plug in the t equals negative 90, this is negative 3 pi over 4 plus 3 pi over 4. So my lower bound should be 0. Yeah, my new lower bound should be 0 here. What about the new upper bound? If I plug in 30 for t, 30 divided by 120 is 1/4. So I've got pi over 4 plus 3 pi over 4. That becomes pi. So I'm going to go ahead and multiply all that stuff out front. Like, well, maybe I'm not going to mess with the pi yet. I'll save the pi for later. But 165 times 120 is 19,800 divided by pi. And then what's the antiderivative of sine? What'd you say?
Cosine?
Nope.
Negative cosine?
There you go. Antiderivative of sine is negative cosine. And then we're going to plug in pi, we're going to plug in 0, we're going to subtract. So what's cosine of pi? Cosine of pi is negative 1. What's cosine of 0? Cosine of 0 is 1, yeah. So we've got negative 1 minus negative 1. That's going to be 2. And so now I can say 2 times 19,800 divided by pi. And that's going to be 12,605. Final answer. So, to answer the question, 30 minutes after kickoff, how many fans are in the stadium? 12,605 fans. And I'll pause for a minute because maybe I should do this for every problem, but I'm not sure if we have to do it for every problem. But I just want to remind you like what the integral means, geometrically. So seeing the picture of what all this is could help. Our function, our rate of change was 165 times sine of pi divided by 120 times t plus 3 pi over 4. I think that was it. Yep. So we got to go find it now. It's probably going to have really large y values because my answer was like 12,000, right? So I might have to zoom out a little bit in the y direction. Okay, maybe I zoomed out a little bit too far in the y direction. And we were really only interested in the time where x was between negative 90 and 30. So this is what we're talking about. And this is not the number of fans in the stadium, right? This is the rate at which fans are entering the stadium in fans per minute. And so if I want the number of fans in the stadium, what we have to do is take the area between the x-axis and the y-axis. And so this area is 12,605. Because if the rate that fans are entering the stadium is a pretty small number, then this area is growing pretty slowly as I pan from left to right. But whenever the rate at which fans are entering the stadium is a really large number, this area is growing really quickly as we pan from left to right. So there's a little bit of a connection, I hope, between the geometric picture and the idea of this rate of change accumulation function. So I don't need to read all these to you, but you guys remember that if I have a function that describes position as a function of time, and I take the derivative with respect to time, I get velocity. And if I take the derivative of velocity, I get acceleration. So we're going to do the same thing now. But now that we can do antiderivatives, we can do a little bit more here. Since velocity is like the rate of change of position, you can think of position as being like an accumulation function of velocity. Like my distance is really what it looks like to accumulate speed over time, if you want to think about that. One day you decide you must get far, far away from Olathe. You get in your car and you drive in a straight line directly away from the city. The following function describes your acceleration in miles per hour squared as a function of time in hours. Suppose you began driving at 15 miles an hour. Find the function that describes your velocity as a function of time. So if I have acceleration given to me, then my velocity function is going to be an accumulation of acceleration. So I'm going to put my acceleration function here on the inside of the integral. And it's kind of like the standard practice to use a different variable for integration. I hope this makes sense to you. Or maybe not, maybe not. Let's try this a different way. Let's say I know that the derivative of velocity is acceleration. So let's start just by finding the antiderivative of acceleration. What's the antiderivative? And maybe first we'd like to distribute that 20. So 20 times 2 is 40, 40 plus 10 is 50. And then 20 times negative t would be negative 20t. That's probably the first step. And then we think, what's the antiderivative of that? Take it one term at a time. What's the antiderivative of negative 20t?
Negative 10t squared.
There you go. You got it. Yeah, so the t becomes t squared, and then I divide by 2, so I get negative 10t squared. And then what's the antiderivative of 50?
50t.
Plus 50t. Do I need anything else, or is that it?
Plus c.
Plus c. And you can check your work. You can take the derivative of velocity and make sure you get acceleration. But that's it. Now, check this out. I'm giving this extra little bit of information that says the velocity at time t equals 0 is 15. So now, this little c can be any real number I want it to be. It can be 0, it can be pi, it can be negative 70. What number should I choose for my little lowercase c? 15. Do you see why it has to be 15? Because if I plug in t equals 0, I've got negative 10 times 0 plus 50 times 0 plus c, and that's got to be equal to 15. So c has to be 15. Okay, so now I've got my velocity function. We can move on and ask, what was my average acceleration? Well, that would mean my velocity at the end minus my velocity at the start divided by the end time minus the start time. So I would have to plug in 6 into my velocity function. So here I am getting out the calculator. My velocity at the end was negative 45. My velocity at the start was 15. So I've got negative 60 over 6, which is negative 10. Average acceleration was negative 10. Suppose you began at a position 0 at time 0. Find the function that describes your position as a function of time. So what color have I not used? We'll use purple. I know that position, when I take the derivative of position, I get velocity. So if I want position, I should take the antiderivative of velocity. So we are going to take the antiderivative of negative 10t squared plus 50t plus 15. What's the antiderivative of negative 10t squared?
Negative 10 over 3 t cubed.
Negative 10 over 3 t cubed. What's the antiderivative of 50t? (25t squared). What's the antiderivative of 15? Plus c. And that c could be anything. The way that I try to figure out what that c is going to be is I'm going to remember that my problem statement told me that we are beginning 0 miles away from Olathe. In other words, p of 0 is 0. So if I plug in t equals 0 for all of these t's, that must mean that c has to be equal to 0 in order to make that work. Okay, what was your average velocity? Average velocity is my position at the end minus my position at the start divided by the end time minus the start time. And so I got to get out my calculator again and figure out what was the position at time t equals 6. Negative 10 over 3 times 6 cubed plus 25 times 6 squared plus 15 times 6 plus 0. That is 270. Remember, the position at the start was 0. So then we divide by 6. Turns out my average velocity was 45 miles per hour. Any questions so far? So earlier, like a few weeks ago, we were doing the same kind of problem, but we were starting with the position function, and then we were taking derivatives to find velocity, we're taking derivatives to find acceleration. This time we're starting with the acceleration function, so working in the opposite direction. We have to take an antiderivative to get velocity, and another antiderivative to get position. When were you driving the fastest? So we're talking about a maximum of velocity. And the max velocity could occur at the start point, right? Or it could occur at the end point. Or it could occur at a stationary point of the velocity function. Right? The maximum velocity would occur at t equals 0 if I started off really fast and I just slowed down the entire time. The maximum velocity could occur at t equals 6 if I start off slow and I'm accelerating the whole time and then I'm hit a maximum velocity at the end. Or another possibility is maybe I'm accelerating, getting faster and faster and faster, and then I start to slow down again. Well, then the point between increasing speed and decreasing speed would be my maximum. So that would be a place where the acceleration is 0. It goes from positive to negative, and this is all continuous. This is all real life, so it kind of has to be continuous. Those are the options, either t equals 0, t equals 6, or whatever value of t gives me a 0 acceleration. So let's look at my acceleration function. And this is the acceleration function, right? Negative 20t plus 50. And that would give me t equals 5 over 2. So what's the velocity at t equals 0? That's actually given to us in our problem statement. Our problem statement said we started off driving 15 miles an hour. What's the velocity at t equals 6? That's right, we found that earlier, and that was negative 45. Now, we need to find the velocity at t equals 5 halves, or t equals 2.5. And so that means I got to find my velocity function, this one right here. And this time I'm plugging in t equals 2.5. So it'll be negative 10 times 2.5 squared plus 50 times 2.5 plus 15. I got 77.5. So when was I driving the fastest? Well, I checked my start point, checked my end point. I checked the stationary points. And it looks like the fastest we were driving was at 2.5 hours when we were driving 77.5 miles per hour. When were we farthest away? So this is now looking for a maximum of the position function. And the maximum of the position could happen at the start time if I were starting far away from Olathe and driving closer to Olathe the whole time, then the maximum could occur at the start. It could occur at the end time if I'm driving away from Olathe the entire time, then I would be farthest away at the end. And then it also could occur at the stationary points of position, which is where the velocity is equal to 0. In other words, it could occur at those times when I was driving away from Olathe, but then I stopped and turned around and started driving back towards Olathe. So we've got to check all of those. Let's find the velocity function. Here it is, negative 10t squared plus 50t. Plus 15. And I'm looking for places where this is equal to 0. And so we could divide everything by 5. But then we still need to use the quadratic formula. So the quadratic formula says t equals negative b over 2 times a plus or minus the square root of b squared minus 4 times a times c divided by 2a. So negative 10 divided by negative 4 is 2.5. Then we've got the square root of 100 plus 3 times 8 plus 24. Square root of 124 divided by 4. So 2.5 plus or minus 2.784. And obviously I don't care about times below 0 because of this in my problem statement. But I would care about the 2.5 plus that number. And so it looks like the only stationary point of the position function that I care about is 5.284. Okay, so let's test all of these out. At t equals 0, my position is 0. That's actually part of the problem statement, right? We found that up in our blue highlight right there. Now, we try t equals 5.284 and t equals 6. By the way, we've already found the position at t equals 6. We did that earlier. 270. That's what we found earlier already. Okay, the last thing we need is we need to take our position function and plug in 5.284. So here's my position function. And we need to plug in 5.284. So, -10 divided by 3 times 5.284 cube plus 25 times 5.284 squared plus 15 times 5.284. My position at time 5 hours, 0.284 is 285.5. So the question, when were we the farthest away? We were the farthest away at time t equals 5.284. Okay, any questions about that one? No?
So then since it decreases, do we just turn around and start heading back at 6
Yep.
hours? All right.
I think that's what you'd find, is that the velocity would be, the velocity ends up negative, right? The velocity ends up at -15. And so it means at some point you stopped and turned around if your velocity goes from positive to negative. I'm trying to make the most of our time. We've got 24 minutes. Let's talk about this one next, and if we've got time, we'll go back. It says, a satellite travels through space in orbit around Earth at a speed of 7,500 meters per second. So here's my satellite. I'll draw a photorealistic satellite for you guys. There we go. And it's cruising. An astronaut wants to catch the satellite. So here's our astronaut. She is traveling at a slower speed, apparently. That must be a typo. I gotta fix that. Make that a little bit faster so she could eventually catch it, right? That would be smart. Oh, never mind. I need to be more patient. I need to read the entire problem first. Okay, it's okay that she's traveling a little bit slower in my problem statement. Because why? She's actually using a booster. I guess she has like a jetpack on. So here's her little jetpack. And it is, blasting her forward so that she is constantly accelerating at 5 meters per second squared. And the distance between her and the satellite is 200 meters. Okay, so there's a lot here. How long will it take her to intercept the satellite? At what speed will she collide with the satellite? And how far will the satellite travel between now and the time it is intercepted? Okay. So we're going to define this quantity here as relative position. P. And it's going to be a function of time. We can call it p of t. The other thing I'm interested in is like, what's their relative velocity? Well, at the start of this whole experiment, their relative velocity is going to be 7,500 minus 7,400. Actually, I should write this the other way. I should write, I don't remember what I said. I don't remember if I wrote it right the wrong first time or not. I'm going to say 7,500 minus 7,400 because if I write it this way, 7,500 minus 7,400, I get a positive number. I get positive 100. And that positive velocity indicates to me that the position is increasing, right? The distance between those two is increasing. So a positive velocity tells me that's a positive rate of change of the distance. I want my distance to be increasing, so I want the velocity to be positive. If I did 7,400 minus 7,500, then it would be negative, but that's not right in this case when they're actually growing farther apart over time. All right. So I'm interested in like, when is she going to hit the satellite? In other words, when is the distance between the two going to be 0? Well, I need a function that describes the distance between those two, and then I'll just find the 0 of the function. To get the function, we are going to begin right at the start, by which I mean acceleration. The satellite is not accelerating. The satellite is traveling at a constant speed, but she's accelerating, and the acceleration is -5. Let's see if that takes a little bit of explaining. The acceleration is constant, so it's not going to be 5t or anything like that. It's just a constant 5 for acceleration. The reason I gave this a -5 is because this is having an effect that would make the relative velocity smaller. If she is speeding up, then the relative velocity between the two objects is actually decreasing. So to make velocity decrease, we need a negative acceleration. If you want a function to be decreasing, you need a negative derivative. So if you want the velocity to be decreasing, we need a negative acceleration. Okay, because her velocity personally is increasing, but the relative velocity between the two objects is going to be decreasing. So now let's find my velocity function. Velocity is the antiderivative of acceleration, so that should be -5t plus c. And since the velocity at time 0 is 100, what is my little lowercase c constant? 100. Okay, now let's take the antiderivative of velocity to give me position, my relative position. So what's the antiderivative of -5t? Yeah. What's the antiderivative of 100? 100t. And then don't forget plus c. Now, remember, what's my relative position at time t equals 0? In other words, what's the distance between the two objects to begin with? 200. So what should be my lowercase c? Yeah, because when I plug in t equals 0 into this position function, I'm getting 0 plus 0 plus c, and 0 plus 0 plus c has to be equal to 200, so c is 200. Now I've got a nice function that describes the distance between these objects as a function of time. So if I want to know when do these objects collide, I'm basically asking when does the distance function equal 0? So I'm going to multiply everything by 2. Because everybody hates a fraction. And then I'm going to use the quadratic formula. So let's sit into our quadratic formula. It's negative b over 2a plus or minus the square root of b squared minus 4 times a times c, which is 4 times 5, 20, 20 times 400. Well, 2 times 4 is 8. And then I collect 3 zeros there. And minus 4ac, that's going to be a positive, because 2 negatives make a positive, divided by 2 times a. So then 200 divided by 10 would be 20. And then we've got plus or minus the square root of 40,000 plus 8,000, so 48,000. And then divide that by 10. I don't care about negative values of t. Right, because in this little experiment, we're saying this is our condition at the start, at t equals 0. We don't know what happened before that. We don't know if you just jumped out of the space shuttle a second before. But that's where we're at. So we forget about the negative values of t in this situation, and we just look at the positives. We say t equals 41.91. That must be the time it takes her to intercept the satellite. And that's what, seconds? Yeah, we're in seconds. So how long does it take her to intercept the satellite? 42 seconds. Second bullet point says, at what speed difference will she collide with the satellite? So I already have a velocity function. And now that I have the time of the collision, we can find that really easily. We just got to plug in negative 5 times 41.91 plus 100. We get negative 109.6. And if we're talking about speed, you know, speed is the absolute value of velocity. And so we are hitting the satellite at 109.6 meters per. That would probably really hurt. Probably would not be very comfortable to collide with a satellite going 109 meters per second. She probably didn't survive that. How far will the satellite travel between now and the time it's intercepted? That's actually an easy question, right? The satellite is traveling at a constant 7,500. So just multiply that speed in meters per second times the number of seconds that it takes. And we get 314,325 meters. 314 kilometers.